Learning objectives. In this chapter, the user would learn the following in detail. Basic concept: hoarding and caching. Cache invalidation. Client-server computing architecture. Transaction models. Query processing. Data recovery. Data dissemination communication asymmetry. Data delivery mechanisms. Broadcast disks. Selective tuning and indexing. Synchronization protocols. Database hoarding. A mobile device cannot store a large database due to memory constraints. Large databases kept on servers, remote computing systems, or networks. Retrieving the required data from a database server during every computation is impractical due to time constraints. A mobile device not always connected to the server or network, neither does the device retrieve data from a server or a network for each computation. Rather, the device caches required specific data which may be required for future computations during the interval in which the device is connected to the server or network. Cache: a list or database consisting of saved items or records at the device, which the device saves for faster access at a later time, rather than reselecting or retuning or refetching data when required. Caching entails saving a copy of select data or part of database from a connected system with large database. Cached data is hoarded in the mobile device database as and when device connects to server or network. Hoarding of cached data in database ensures that even when device is not connected to a network or server, data is instantly available for computing. May be done at application tier 1. Two architectures shown in above figure belong to class of one-tier database architecture. Some examples are downloaded ringtones, music and video clips. Figure A. API at mobile device sending queries and retrieving data from a local database tier 1. Figure B. API at mobile device retrieving data from database using DB2E tier 1. IBM DB2 every place. DB2E is a relational database engine. Needs memory of about 100 KB. Designed to reside at the device. Supports databases of sizes up to 120 MB. Enterprise server employing DB2 delivers and synchronizes local copies of data contents at mobile devices. Synchronization means that if a data record is modified at the server, then the copy of that record at the client device also changes accordingly. Supports J2ME and most mobile device operating systems, including Windows CE, Palm OS, Symbian V6 and handheld computer operating system Win32, Linux, QNX and Neutrino. DB2E synchronizes with DB2 databases at the synchronization application or enterprise server. Hoarding multi-tier databases. Database architecture shown in the above figure is for two-tier or multi-tier databases. Database resides in remote servers and copies of these databases are cached at the client tiers. This type of architecture is known as Client-server computing architecture. Computing API at the mobile device first tier uses the local cached data records using computing architecture. Server retrieves data from Tier 2 or Tier 3 and transmits the records to Tier 1 using specific business logic. It sends and synchronizes local copies at the device. These local copies function as device caches. Advantage of hoarding. No access latency, delay in retrieving the queried record from the server over wireless mobile network. The client device API has instantaneous data access to hoarded or cached data. After a device caches the data distributed by the server, the data is hoarded at the device. Disadvantage of hoarding. Need to maintain the consistency of the cached data with the database at the server. Data caching. Cache access protocols. Client device caches the pushed disseminated data records from a server. Caching leads to a reduced access interval as compared to the pull on-demand mode of data fetching. Also reduces the dependence on pushing precedence at the server. Caching of data can be based on pushed hot records. Cost-based data replacement or caching. Caching can be based on the ratio of two parameters, access probability of and pushing rates from the server for each record. Access probability of each record and its comparison with portability of other records is often unpredictable in the wireless environment. Alternative method is that the least frequently pushed records and pushed records having larger access time are placed in database at the device. This access method therefore uses the ratio of two parameters, average access time between two successive instances of access to the record and pushing rate for the record. Prefetching. Alternative to caching of disseminated data. Process of prefetching entails requesting for and pulling records that may be required later. Keeping future needs in view, client device can prefetch data instead of caching from the pushed records. Reduces server load. Reduces the cost of cache misses. The term cost of cache misses refers to the time taken in accessing a record at the server in case that record is not found in the device database when required by the device API. Data dissemination broadcast models. Data dissemination, transmission of records from a server. Record, set of bits or bytes. Bucket, smallest logical unit of a single broadcast. Cyclic repetition and broadcasting disk model. A record is assumed to be placed on a circular disk from 0 degree to 360 degree. A hypothetical disk revolves and the angle changes from 0 degree to 360 degree. The entire bits in the record get pushed through a hypothetical reading head over the disk. The head continuously reads each bit of a record just beneath it and broadcasts it instantaneously on the wireless network. During next revolution, each bit in the record's position from 0 to 360 degree broadcast once again in the same sequence as in the earlier revolution. In case a device misses a record in first revolution, it can cache the same in next or any of the successive revolutions. Dissemination-based data delivery using broadcast disk. Proposes a mechanism called broadcast disk to provide database access to mobile clients. Server continuously and repeatedly broadcasts data to a mobile client as it goes by. Multiple disks of different sizes are superimposed on the broadcast medium. Exploits the client storage resources for caching data. Server broadcast programs. Data server must construct a broadcast program to meet the needs of the client population. Server would take the union of required items and broadcast the resulting set cyclically. Single additional layer in a client's memory hierarchy, flat broadcast. In a flat broadcast, the expected wait for an item on the broadcast is same for all items. Figure 1 shows a flat broadcast program. Broadcast disks are an alternative to flat broadcast. Broadcast is structured as multiple disks of varying sizes, each spinning at different rates. For uniform access probabilities, a flat disk has the best expected performance. For increasingly skewed access probabilities, non-flat disk programs perform better. Multi-disk programs perform better than the skewed programs. Figure shows flat broadcast, skewed broadcast, and multi-disk broadcast. Generating a multi-disk broadcast. Number of disks NUM_disks determine the number of different frequencies with which pages will be broadcast. For each disk, the number of pages and the relative frequency of broadcast REL_FREQI are specified. Figure shows deriving a server broadcast program. Client cache management. Improving the broadcast for one probability access distribution will hurt the performance of other clients with different access distributions. Therefore, the client machines need to cache pages obtained from the broadcast. With traditional caching, clients cache the data most likely to be accessed in the future. With broadcast disks, traditional caching may lead to poor performance if the server's broadcast is poorly matched to the client's access distribution. In the broadcast disk system, clients cache the pages for which the local probability of access is higher than the frequency of broadcast. This leads to the need for cost-based page replacement. One cost-based page replacement strategy replaces the page that has the lowest ratio between its probability of access P and its frequency of broadcast X, PIX. PIX requires the following: perfect knowledge of access probabilities, comparison of PIX values for all cache resident pages at cache replacement time. Another page replacement strategy adds the frequency of broadcast to an LRU style policy. This policy is known as LIX. LIX maintains a separate list of cache resident pages for each logical disk. Each list is ordered based on an approximation of the access probability L for each page. A LIX value is computed by dividing L by X, the frequency of broadcast. The page with the lowest LIX value is replaced. Tree fetching. An alternative approach to obtaining pages from the broadcast. Goal is to improve the response time of clients that access data from the broadcast. Methods of prefetching. Tag team caching. Prefetching heuristic. Tag team caching. Pages continually replace each other in the cache. For example, two pages X and Y being broadcast, the client caches X as it arrives on the broadcast. Client drops X and caches Y when Y arrives on the broadcast. Simple prefetching heuristic performs a calculation for each page that arrives on the broadcast based on the probability of access for the page P and the amount of time that will elapse before the page will come around again T. If the PT value of the page being broadcast is higher than the page in cache with the lowest PT value, then the page in cache is replaced. Read-write case. With dynamic broadcast, there are three different changes that have to be handled. Changes to the value of the objects being broadcast. Reorganization of the broadcast. Changes to the contents of the broadcast. Cache invalidation. Caching invalidation mechanisms. Access protocol's cached record at the client device may be invalidated due to expiry or modification of the record at the database server. Cache invalidation, a process by which a cached data item or record becomes invalid and thus unusable because of modification, expiry or invalidation at another computing system or server. Cache invalidation mechanisms are means by which the server conveys this information to client devices. Figures below depict the similarity between architecture of distribution of database at mobile device caches and cache and shared memory data architecture in multiprocessor systems. This similarity extends to the cache invalidation mechanism. Caching invalidation mechanisms used to synchronize data at other processors when cached data is written, modified by a processor in multiprocessor system and active in case of mobile devices having distributed copies from server. Caching. Figure shows distributed data caches in mobile devices. Figure shows similar architecture for a distributed cache memory in multiprocessor systems. MESI protocol. Cache consists of several records. Each record is called a cache line. Copies of these can be stored at other devices on servers. Cache at mobile devices or server databases can be assigned one of four possible tags indicating the state. M. Modified after rewriting. E. Exclusive. S. Shared. I. Invalidated after expiry or when new data becomes available. Cache invalidation mechanisms under the MESI protocol entail that each record line in a cache has a tag to specify its state at any given instant, and the tag is updated, modified as soon as the state of the record changes. MESI protocol state. States indicated by various tags are as follows. M tag indicates modified state. Means that device cache or server has rewritten a database record. State is to be noted on access initiated by the client. E tag indicates the exclusive state. Means data record is for internal use, cannot be used by any other device or server. S tag indicates shared state. Means data record can be used by others. I tag indicates invalidated state. Means server database no longer has a copy of record which was shared. This state is reported by the server to the clients and noted by clients. Figure shows 4 possible states M, E, S or I of a data record I at any instance at the server database and device J cache. Cache consistency. Important factor for cache maintenance, also called cache coherence, requires a mechanism to ensure that a database record identical at the server as well as at the device caches and that only the valid cache records are used for computations. If database server changes a data record of which one or more clients have copies, then the server record is invalidated, forcing all client devices to not use the data further their cache copies. New updated copies can be got on request. There are 4 possible invalidation mechanisms: stateless asynchronous, stateless synchronous, stateful asynchronous, stateful synchronous. Stateless asynchronous. Device cache states are not maintained at the server. The server advertises invalidation report. On receiving an invalidation report, the client requests for or caches the new data record. Advantage of the asynchronous approach: no frequent unnecessary transfers of data reports. Mechanism more bandwidth efficient. Disadvantages: every client device gets an invalidation report whether that client requires that copy or not. Client devices presume that as long as there is no invalidation report, the copy is valid for use in computations. Therefore, even when there is link failure, the devices may be using the invalidated data and the server is unaware of state changes at the clients after it sends the invalidation report. Stateless synchronous. Device cache states are not maintained at the server. The server periodically advertises invalidation report. The client requests for or caches the data on receiving the invalidation report. If no report is received till the end of the period, the client requests for the report. Advantage of synchronous approach. Client devices receive periodic information regarding invalidity and thus validity of the data caches. The periodic invalidation reports lead to greater reliability of cached data as update requests for invalid data can be sent to the server by the device client. This also helps the server and devices maintain cache consistency through periodical exchanges. Disadvantage of the synchronous approach. Unnecessary transfers of data invalidation reports take place. Every client device gets an advertised invalidation report periodically, irrespective of whether that client has a copy of the invalidated data or not. During the period between 2 invalidation reports, the client device assumes that as long as there is no invalidation report, the copy is valid for use in computations. Stateful asynchronous. Device cache states are maintained at the server. The server transmits invalidation report to concerned devices. The client requests for new data on receiving the invalidation report and sends its new state after caching new record from the server. Advantage of the stateful asynchronous approach. Server keeps track of the state of cached data at the client device. This enables the server to synchronize with the state of records at the device cache and keep the home locating cache HLC updated. Only the affected clients receive the invalidation reports and other devices are not flooded with irrelevant reports. Disadvantage of the asynchronous stateful. Client devices presume that as long as there is no invalidation report, the copy is valid for use in computations. Therefore, when there is a link failure, then the devices use invalidated data. Stateful synchronous. Device cache states maintained at the server. The server periodically transmits invalidation report to the concerned devices. The client requests for new data on receiving the invalidation report and sends its new state after caching the new data. If no report is received till the end of the period, the client requests for the report. Advantage of the stateful synchronous approach. Reports identifying invalidity and thus indirectly of validity at periodic intervals, and that the server also periodically updates the client cache states stored in the HLC. Enables to synchronize with the client device when invalid data gets modified and becomes valid. Each client be periodically updated of any modifications at the server. When the invalidation report is not received after the designated period and a link failure is found at the device does not use the invalidated data. Instead, it requests the server for an invalidation update. Disadvantage: high bandwidth requirement to enable periodic transmission of invalidation reports to each device and updating requests from each client device. Data cache maintenance in mobile environments. Pulling: a request sent to the server for data records. Access latency: time taken for application to access a record. Caching and holding a record at a device reduces access latency to 0. Data cache maintenance necessary to overcome access latency. Data cache inconsistency means that data records cached for applications are not invalidated at the device when modified at server but not modified at device. This can be maintained by 3 methods given below. Cache invalidation mechanism, server-initiated case. Polling mechanism, client-initiated case. Time-to-live mechanism, client-initiated case. Data cache maintenance in mobile environments. Cache invalidation mechanism, server-initiated case. Server sends invalidation reports on invalidation of records asynchronous or at regular intervals synchronous. Polling mechanism, client-initiated case. Polling means checking from the server the state of data record, whether the record is valid, invalid, modified, or exclusive state. Each cached record copy polled checked whenever required. The device connects to the server and finds out data record copy at the device become invalid or has been modified at the server. If modified or invalidated, then the device requests for the modified data and replaces earlier copy. Time-to-live mechanism, client-initiated case. Each cached record assigned a TTL, time to live. The TTL assignment is adaptive, adjustable, previous update intervals of that record. After the end of the TTL, the client device polls for invalid or modified state. If invalid or modified state found, then the device requests the server to replace. When TTL is set to 0, the TTL mechanism is equivalent to the polling mechanism. Web cache maintenance in mobile environments. Web cache, a device, stores web server data and maintains it in a manner similar to cache maintenance for server data. Web cache maintenance is necessary in a mobile environment to overcome access latency in downloading from websites due to disconnections. Web cache consistency can be maintained by following methods. Time to live TTL mechanism, client-initiated case, identical to data cache maintenance. Power-aware computing mechanism, client-initiated case. Power-aware computing mechanism, client-initiated case. Each web cache maintained at the device can also store the CRC, cyclic redundancy check bits. Assume that there are n cached bits and n CRC bits, and n is greater than n. Server also stores n CRC bits. Consistency between the server and device records, the CRC bits are both identical. Else, the corresponding CRC bits at the server modifies. After the TTL expires or on demand for the web cache records by the client API, the cached record CRC pulled and obtained from the website server. If the n at server found to be modified and the change is found to be much higher than a given threshold, that is a significant change, then the modified part of the website hypertext or database is retrieved by the client device for use by the API. Client-server computing architecture. A network architecture where a node, computers and computing devices is either a client or server. Client node, mobile devices, runs application software which depends on server node resources. Server node has larger resources and computing power than client nodes, different from peer-to-peer architecture. Client-server computing. Distributed computing architecture with two types of nodes, clients and servers. A client requests the server for data or responses. The client can either access the data records at the server or cache these records through broadcast or distribution from the server. An n-tier architecture where n is equal to 1 or 2 on the same computing system, not on a network, then the number of tiers n is equal to 1. When the client and the server are on different computing systems on the network, then n is equal to 2. Connecting to other systems provide additional resources to the server for the client, then n is greater than 2. N is greater than 1 means that the client device at tier 1 connects to the server at tier 2, which in turn may connect to other tiers 3, 4 and so on. A command interchange protocol example, HTTP, is used for obtaining client requests at server or server requests at client. Two-tier client-server architecture. Figure shows application server and two-tier client-server computing architecture. Local copies of 1 to j of database holding at the mobile devices on client request. A specific application may require an application server to send a local copy of data to multiple devices. This enables running of application independently on the devices without the need for a runtime retrieval. Various APIs synchronize with each other. Synchronization means that when copies at the server end modifies, the cached copies accordingly get modified. The APIs are designed independent of hardware and software platforms as far as possible, as different devices may have different platforms. 3-tier client-server architecture. The application interface, the functional logic, and the database are maintained at 3 different layers. The database is associated with the enterprise server tier 3. Only local copies of the database exist at mobile devices. Database is at the back-end system of an enterprise company that holds IBM DB2, Oracle, and other databases. Server at Tier 2 connects to the enterprise server through a connecting protocol. The enterprise server connects the complete database on different platforms, for example, Oracle, XML, and IBM DB2. Data records at Tier 3 are sent to Tier 1 through a synchronization application server at Tier 2. Synchronization application server has synchronization and server programs for retrieving data records from enterprise Tier 3 using business logic. Enterprise Tier connects to a database using connectivity protocol and sends database records as per business logic. Connectivity of the synchronization application server to the enterprise server is by RPC, RMI, JNDI, or IIOP protocols. In case the application client at Tier 1 connects to Tier 2 using the Internet, the connectivity uses HTTP or HTTPS. Figure shows database record copies of database at the mobile devices using 3-tier architecture. Figure shows mobile device with J2ME or BREW platform, an OS and database having local copies. N-tier client-server architecture. When n is greater than 3, then the database is presented at the client through in-between layers. Figure shows a 4-tier architecture in which a client device connects to a data presentation server at Tier 2. The presentation server then connects to the application server Tier 3. The application server can connect to the database using the connectivity protocol and to the multimedia server using Java or XML API at Tier 4. Data delivery mechanisms. Data dissemination means data delivery from a server or remote computing system or network. Delivery mechanisms are classified as push-based mechanisms or publish-subscribe mode, pull-based mechanisms on demand mode, hybrid mechanisms, hybrid mode. Data delivery mechanisms. Push-based mechanisms. Server pushes data records from a set of distributed computing systems. Examples of distributed computing systems are advertisers or generators of traffic congestion, weather reports, stock codes, and news reports. Figure shows a server or computing system pushing the data records from a set of distributed systems. Push-based mechanisms. Push without any demand mode. Data records are pushed to mobile devices by broadcasting. Publish-subscribe mode. The data is pushed as per the subscription for a push service by a user until device unsubscribes the service. Push-based mechanisms function in following manner. Pushing algorithm. Select a structure of data records to be pushed. An algorithm provides an adaptable multi-level mechanism that permits data items to be pushed uniformly or non-uniformly after structuring them according to their relative importance. Pushing intervals. Data pushed at selected time intervals using an adaptive algorithm. Pushing only once saves bandwidth. However, pushing at periodic intervals is important because it provides the devices that were disconnected at the time of previous push with a chance to cache the data when it is pushed again. Pushing bandwidths. Bandwidths adapted for downlink for pushes using an algorithm. Periods of pushing. The same fixed periods can be used for pushing all records, but usually higher bandwidth is allocated to records having higher number of subscribers or to those with higher access probabilities. Stopping pushes. A mechanism also adopted to stop pushes when a device is handed over to another cell. Advantage of push-based mechanisms. Enable broadcast of data services to multiple devices. Server is not interrupted frequently by requests from the mobile devices. Best option for the server as they prevent server overload which may occur due to flooding of device requests. Disadvantage of push-based mechanisms. Dissemination of unsolicited, irrelevant or out-of-context data. User may not be interested in the disseminated data and may be inconvenienced. Data delivery mechanisms. Pull-based mechanisms. User device or computing system pulls the data record from the service provider's application database server or from a set of distributed computing systems. On-demand request mode. Use of distributed computing systems for pulling music album server, ringtone server, video clip server, or bank account activity server, etc. There may be selective response from the server, which means server transmits data packets for a response selectively. Transmission is done after client authentication, verification, or subscription account check. Figure below shows a mobile device pulling the data records from a server or set of distributed systems. Pull-based mechanisms. Pulling bandwidth. Used for the uplink channel and depends upon the number of pull requests. Assume that an uplink bandwidth of 19.2 kbps and service provider's application distribution system server accepts 384 kbps. Then only 20 pull requests can be used at 19.2 kbps. Number of pull requests is larger, the link channel bandwidth lowered to 9.8 kbps or 4.8 kbps. Similarly, the service provider's application distribution system adapting to the bandwidth required for serving the request downlink in case the server is unable to deliver the response in a reasonable period. Pull threshold. Threshold limits the number of pull requests in a given period of time. Controls the number of server interruptions. Prevent device from pulling from a cell. A mechanism is adopted to prevent access when handed over to another cell. On device handoff, the subscription is cancelled or passed on to the new service provider system. Advantage of pull-based mechanisms. No unsolicited or irrelevant data arrives at the device. Relevant data disseminated only when the user asks for it. Best option when the server has very little contention and is able to respond to many device requests within expected time intervals. Disadvantage of pull-based mechanisms. Server faces frequent interruptions and queues of requests at the server may cause congestion in case of sudden rise in demand for certain data records. the energy and bandwidth required for on-demand mode when sending the request for hot items and temporal records changing with time, is large. The number of server interruptions and uplink bandwidth requirement may increase 1,000 times in the pull mode for hot records, example, World Cup football score. A large number of devices making requests to the service provider choke the network. The server is flooded with interruptions. Data delivery mechanisms, hybrid-based mechanisms. Integrates pushes and pulls. Interleaved push and pull IPP mechanism. The user device or computing system pulls as well as receives the pushed data records. The devices use the back channel to send pull requests for records which are not regularly pushed by the front channel. The front channel uses algorithms modeled as broadcast disks and sends the generator interleaved responses to the pull requests. Examples: a distributed computing system advertising and selling music albums. The advertisement push and the mobile devices pull for buying the album. Figure below shows user device a computing system pulling as well receiving the pushed data records. Hybrid mechanisms function in the following way. There are two channels between devices and server, one for pushes by front channel and other for pulls by back channel. Bandwidth is shared and adapted between the two channels. It is adapted in downlink and uplink channels depending upon the number of active devices receiving data from the server and the number of devices requesting data pulls from the server. An algorithm adaptively chops the slowest level of the scheduled pushes successively into large number of pieces. Assume that at the slowest level, m data records each of length n bits are broadcast and pushed at successive interval of time t's each. The bandwidth used by these records is m into n into 1 by ts bps. Advantage of hybrid-based mechanisms. The number of server interruptions and queued requests are significantly reduced. Disadvantage of hybrid-based mechanisms. IPP, however, does not eliminate the typical server problems of too many interruptions and queued requests. The adaptive chopping of the slowest level of scheduled pushes. Communication asymmetry. GSM network data transmission rates go up to a maximum of 14.4 kbps for both uplink and downlink, and communication is symmetric as it is used only for voice communication. Most mobile communication between the mobile device and static computer system is intrinsically asymmetric. Asymmetric means data transfer rates may vary for uplinks and downlinks. Example: I modes to understand asymmetry in communication. Used for multimedia transmission, internet access and voice communication. Base station provides downlink 384 kbps. Uplink from the device is restricted to 64 kbps. Communication between base station and mobile device is thus asymmetric. Reasons behind asymmetry. Power. Mobile devices have limited power resources. Faster data transmission rates for long intervals of time need greater power dissipation from the devices. So mobile devices transmit a lesser data rates than the server. Bandwidth. Bandwidth is the downstream from the server to device is much larger than the one in the upstream from the device to server. A device may be allocated limited bandwidth because large number of devices access the network at an instance. Interference and time dispersion. In wireless signals, this results in signal distortion and transmission errors at receiver end. Also lead to path loss and signal fading, causing data loss at high data rates. Access latency. Greater access latency in wireless networks than in wired networks, as data loss has to be taken care by repeat transmissions. Transmission errors may have to be corrected. Errors cannot be taken care of by appending additional bits such as forward error correction bits. Storage capacity. Mobile devices have low storage capacity, cannot hold large databases. Accessing data online not only has a latency period but also dissipates bandwidth resources of the device. Communication asymmetry in uplink and downlink in a mobile network
is shown in the below picture.
Broadcasting corresponds to unidirectional downlink from the server to the devices. Unicast communication. Unicast means the transmission of data packets in a computer network such that a single destination receives the packets. This destination, generally the one which has subscribed to the service. Mobile TV, an example of unidirectional unicast mode of broadcasting. Each device receives broadcast data packets from the service provider's application distribution system. Application distribution system broadcasts data of text, audio, or video services. Broadcasting architecture. Figure below shows broadcasting architecture. Data recovery process. Number of reasons warranting database recovery: media failure, system failure, transaction abortion, data destruction due to intentional external attack, due to careless handling, user carelessness. Data may also be destroyed due to destruction of the physical media holding the data. Logical program errors and a transaction may not materialize. Loss of main memory due to system errors, hardware or software. Data is non-recoverable in case of media failure, intentional attack on the database, and transactions logging data or physical media destruction. Data recovery is possible in other cases. Recovery management architecture. Recovery manager recovers or aborts a transaction using the logged entries. Recovery manager log file. Each instruction for a transaction for update, insertion, deletion, replacement and addition log. Database read instructions are not logged. Log files stored at a different storage medium. Log entries flushed out after the final stable state database is stored. Logged entry fields. Transaction type: begin, commit or rollback transaction. Transaction ID. Operation type: object on which the operation performed. Pre-operation and post-operation values of the object. Checkpoint-based recovery uses the checkpoints for operations on the data during a set of transactions. Recovery always made by backscanning the logged records. A checkpoint-based data recovery procedure defines the stage up to which the backscanning of logged operations in the secondary storage is to be done. Aries algorithm. used for recovering lost data. Basic steps are: identify all dirty records, records written again after the operation restarted in the buffer starting from last checkpoint. Redo all buffered operations logged in the update log to finish and make final page. Undo all write operations and restore pre-transaction values. Recovery models used in data recovery process. Full recovery model creates backup of database and incremental backup of changes. All transactions are logged from last backup taken for database. Bulk logged recovery model logs and takes backup of bulk data record operations but not full logging and backup. Size is kept to minimum to improve performance. Can recover database to the point of failure by restoring database with bulk transaction log file backup. Unlike full recovery where all operations are logged. Simple recovery model prepares full backups but incremental changes are not logged. Can recover the database to most recent backup. Query processing. During a transaction with a database, queries are sent to read and get the records from the database. Consider two sets of database records, contacts and saved numbers. Contacts stores the rows of records consisting of first character, first CHAR of name, contact name, CNAME and contact telephone number, CTELNUM. Querying of record in contacts can be using first CHAR, CNAME or CTELNUM. Dial numbers stores the rows of records consisting of dialing sequence number, SEQNUM, time of call, CTIME, and dial telephone number, DTELNUM. A record of dial numbers can be searched by SEQNUM, CTIME, or DTELNUM. SQL query. Select CNAME, CTELNUM from contacts, dial numbers, where contacts dot first CHAR is equal to R and contacts dot CTELNUM is equal to dial numbers dot DTELNUM. Efficient processing of queries needs optimization of steps. Query processing means making a correct as well as efficient execution strategy by query decomposition and query optimization. A relational algebraic equation defines a set of operations needed during query processing. Optimization for efficient processing. Based on cost, number of micro operations in processing by evaluating the cost of sets of equivalent expressions. Based on a heuristic approach consisting of the following steps. Perform the selection steps and projection steps as early as possible and eliminate duplicate operations. The query optimizer employs query processing plan generator, query processing cost estimator. In order to provide an efficient plan for query processing, plan means a tree-like structure of relational algebraic operations for a given equation. Relational algebraic equation for query processing. Queries are sent for a read operation during a transaction with database. Result set of records for the query is extracted from the database. A relational algebraic equation defines a set of operations using the below symbols, which represents projection operation, selection operation, AND operation, cross-check and matching operation. Selective tuning and indexing technique. Why selective tuning? Purpose of pushing and adapting to a broadcast model is to push records of greater interest with greater frequency in order to reduce access time or average access latency. Mobile device does not have sufficient energy to continuously cache the broadcast records and hoard them in its memory. Device dissipates more power if it gets each pushed item and caches it. Therefore, it should be activated for listening and caching only when it is going to receive the selected data records or buckets of interest. Switches to idle power down mode during remaining time intervals, that is, when the broadcast data buckets or records are not of its interest to save energy. Selective tuning is a process by which client device selects only the required pushed buckets or records, tunes to them, and caches them. Tuning means getting ready for caching at those instants and intervals when a selected record of interest is broadcast. Broadcast data structure has overhead. Overhead means additional information which facilitates indexing, which in turn facilitates tuning at the device. Example of a broadcasting mechanism. N records R0 to Rn-1 interleaved and broadcast as in a multi-disc model. Only the records Ri and Rj are of interest and required by applications at a device. The broadcast disc broadcasts Ri and Rj thrice and once respectively, as the subscription probability of Ri is 3 times that of Rj. The record Ri is partitioned into k buckets Bi0 to Bik-1. The records Rj is partitioned into k buckets Bj0 to Bjk-1. Each bucket has equal length LB, which means equal number of bits, and the devices takes identical time IB into TS to cache each bucket's data. Ts, the time interval between successive bits. In addition to data, each broadcast cycle broadcasts a directory, hash key or index, which is the overhead prefixed by server before the data. Selective tuning. Device selects only the buckets of Ri and Rj which are of interest and receives the signals only during first, second or third instances of Ri or during instances of Rj, that is, during the intervals Ti0 to Tik-1, Tj0 to Tjk-1 of broadcasting of Bi0 up to Bik-1, Bj0 up to Bjk-1 respectively. In the remaining intervals, when either the other records which are not of interest are being broadcast or when record of interest is already cached in an earlier broadcast cycle, the device remains idle. During this period, it does not dissipate power and hence saves energy. Access time T-axis. The time interval between pull request from device and reception of response from broadcasting or data pushing or responding system. Two important factors affect T-axis. Number and size of records to be broadcast, greater N and N greater will be T-axis. Directory or cache miss factor. Selective tuning and indexing technique. Some of the techniques or methods used are index-based method using offsets, IM index method, distributive index-based method, flexible indexing method, directory method, hash-based method, temporal addressing, broadcast addressing. Index-based method using offsets. Indexing is another method for selective tuning. Indexes temporarily map the location of the buckets. A broadcast cycle, a number called index, can be first sent. It specifies the location of the bucket or record. Index B first sent. It specifies the location of the bucket or record. Consider a simple example. Let index be 20 at the beginning of a broadcast cycle. It specifies that 20th bucket is of interest and is sent to the device in response to previous subscription. Offset. Offset means a value to be used by the device along with the present location and calculate the wait period for tuning to the next bucket. All buckets have an offset to the beginning of the next indexed bucket or item. Indexing. Another method of selective tuning. Indexes temporarily map the location of the buckets, a technique in which each data bucket, record or record block of interest is assigned an index at the previous data bucket, record or record block of interest to enable the device to tune and cache the bucket after the wait as per the offset value. At each location, besides the bits for the bucket in record of interest data, an offset value may also be specified there. While an index maps to the absolute location from the beginning of a broadcast cycle, an offset index is a number which maps to the relative location after the end of present bucket of interest. The server transmits this index at the beginning of a broadcast cycle as well as with each bucket corresponding to date of interest to the device. Disadvantage of using index: extends the broadcast cycle and hence increases t-axis. IM index method. An index I transmits m times during each push of a record. An algorithm is used to adapt a value of m such that it minimizes access, caching, latency in a given wireless environment, which may involve frequent or less frequent loss of index or data. Index format is adapted to with the suitable m chosen as per the wireless environment. This decreases the probability of missing I and hence the caching of the record of interest. If m is chosen small, then the power dissipated by device is less. If m decrease, the chances that the cache be missed go up and the data access latency increases. The value of m therefore needs to be optimized, which can be done by employing an algorithm as stated earlier. Indexing IM reduces time taken for tuning by the client devices and thus conserves their power resources. When index I is repeated m times, the access latency increases significantly even though the cache miss probability reduces drastically. Distributed index-based method. Distributed index-based method is an improvement on the IM method. In this method, there is no need to repeat the complete index again and again. Instead of replicating the whole index m times, each index segment in a bucket describes only the offset I of data items which immediately follow. Each index I is partitioned into two parts, I and I. I consists of unrepeated k levels subindexes which do not repeat. I consists of top j repeated levels subindexes. Flexible indexing method provides dual use of parameters, use of ISEG or IREC in an index segment to tune to the record or buckets of interest. also provides multi-parameter indexing. Example, use of ISEG, IREC or IB in an index segment to tune to the bucket of interest. For M sets of records called segments, a set of binary bits defines the index parameter ISEG. A local index is then assigned to specific record. Only local index ISEG or IB is used in ILOC M. Number of bits in a local index is much smaller than that required when each record is assigned an index. Directory method. Broadcasting a directory as overhead at the beginning of each broadcast cycle. If interval between the start of the broadcast cycles is T, then the directory broadcasts at each successive intervals of T. A directory can be provided which specifies when a specific record or data item appears in data being broadcasted. A device has to wait for directory consisting of start sign, pointers for locating buckets or records, and end sign. Then it has to wait for the required bucket or record before it can get tuned to it and start caching it. Tune time (T-tune) is the time taken by the device for selection of records. Hash-based method. Hash is a result of operations on a pair of key and record. Advantage of broadcasting a hash is that it contains fewer bits compared to key and record separately. Operations are done by a hashing function. Hash is broadcast from server end and at device end. A key is extracted by computations from data in the record by operating data with a function called hash function. This key is called hash key. Hash-based method entails that the hash for the hashing parameter hash key broadcast. Each device receives it and tunes to the record as per the extracted key. In this method, the records that are of interest to a device or those required by it cached from the broadcast cycle by first extracting and identifying the hash key which provides the location of the record. Temporal addressing. A technique used for pushing in which instead of repeating I several times, a temporal value is repeated before a data record is transmitted. There can be effective synchronization of tuning and caching of the record of interest in case of non-uniform time intervals between the successive bits. The device remains idle and starts tuning by synchronizing as per the temporal information for the pushed record. Temporal information gives the time at which cache is scheduled. Broadcast addressing uses a broadcast address similar to IP or multicast address. Each device or group of devices can be assigned an address. The devices cache the records which have this address as the broadcasting address in a broadcast cycle. This address can be used along with the pushed record. A device uses this in place of the index I to select the data records or sets. Broadcast address can be repeated before a data record is transmitted as an alternative to repeating I several times. Advantage of this is that the server addresses to a specific device or specific group of devices. Synchronization protocols. Protocol used for communication of data between two nodes of a computing system. Also, at each layer of communication, a distinct protocol can be used when communicating data between two layers of a computing node. Synchronizer can deploy different protocol layers for communicating to different devices and computers, and also use the protocol layers for communicating to the personal area and remote area devices and computers. Figure below shows synchronization protocols for the PIM, email and the application data. Bluetooth protocol. A self-discovery protocol used for synchronization among mobile devices and Bluetooth-enabled PCs in a wireless personal area network. A connection-oriented protocol using Bluetooth Object Exchange (OBX), a protocol for transport layer in Bluetooth, can be used for one-to-one or one-to-many communication over short distances. Discovers whether nearby personal area device is a Bluetooth protocol-based communicating device. A Bluetooth-enabled device sets up an ad hoc network with the Bluetooth-enabled devices and computing systems. APIs for the PIM, email, and customized device applications deploy a client, software for sending requests for response from the other node, computer or device, and an engine, software for driving the requests of the client and receiving responses from the server for the client. Figure below shows synchronization between Bluetooth-enabled computer and a mobile device. Synchronization using SYNC-ML. Synchronization between the client and server can be carried out through SYNC-ML codes at the SYNC-ML client and SYNC-ML engine by sending the messages in the given sequence. Sequence of messages: connect, put to put the response to the request or get to get the response to the request, abort to abort the connection. Synchronization using Bluetooth Active Sync partnership. In this kind of partnership, the device uses Bluetooth protocol synchronization and the PC uses Active Sync. For establishing the partnership for synchronization, the Bluetooth device port is first configured as a virtual COM port because the connected server for data is not a Bluetooth device but an Active Sync PC port. Later, the Bluetooth device and PC synchronize through Active Sync. Bluetooth device synchronizes PIM data, calendar, email, business card, text messages, and phone book with the Active Sync device or a device which is not Bluetooth enabled through the virtual COM port. Similarly, a virtual USB port can be configured at the Bluetooth device. IRDA protocol. Infrared Data Association (IRDA) is an infrared-based synchronization of mobile devices and computers within the same room. Specifications include connection-oriented or connectionless protocols. IRDA specifies 5 levels of communication: minimum, access, index, sync, and sync-ML levels 1 to 5. Synchronization can be used to synchronize PIM data, calendar, email, business card, text messages, etc. Wireless Application Protocol WAP 2.0. A protocol for wireless synchronization of WAP client computers and WAP servers. Synchronization through SYNC-ML codes binding over the WAP application layer client or server. WAP Gateway connects WAP clients to HTTP servers which serve Internet websites. The HTTP layer in TCP/IP protocol suite is an application layer protocol used when connecting to Internet in a wired network. WSP Wireless Session Protocol layer in WAP 2.0. An application layer protocol when connecting to the Internet in a wireless network. SYNC-ML codes bind with WSP for Internet connectivity. Transaction models. Database transaction models. Transaction means execution of interrelated instructions in a sequence for a specific operation on a database. Database transaction models must maintain data integrity and must enforce a set of rules called ACID rules. ACID rules permit concurrent running of multiple threads program tasks. acid rules: atomicity, consistency, isolation, durability. Atomicity. All operations of a transaction must be complete. In case a transaction cannot be completed, it must be undone, rolled back. Operations in a transaction are assumed to be one indivisible unit, atomic unit. Consistency. A transaction must be such that it preserves the integrity constraints and follows the declared consistency rules for a given database. Consistency means the data is not in a contradictory state after the transaction. The amount transferred must be subtracted from account A and added into account B. Consistency means that the sum total of the balances in accounts A and B is the same as it was before the transaction. Isolation. If two transactions are carried out simultaneously, there should not be any interference between the two. Further, any intermediate results in a transaction should be invisible to any other transaction. Durability. After a transaction is completed, it must persist and cannot be aborted or discarded. For example, in a transaction entailing transfer of a balance from account A to account B, once the transfer is completed and finished, there should be no rollback. ADO.NET Active X Data Object in .NET Transaction Model. This can be used to access the data and data services and to modify the data stored in relational database systems. ADO.NET Transaction Model permits 3 transaction commands. Begin transaction. It is used to begin a transaction. Any operation after begin transaction is assumed to be a part of the transaction till the commit transaction command or the rollback transaction command. Commit. Used to commit transaction operations that were carried out after begin transaction command and up to this command. All statements between begin transaction and commit must execute automatically. Rollback. Used to roll back transaction in case an exception is generated after begin transaction command. ADO.NET Transaction Model. Caching an exception. When a section of code is executed, an exception condition denoted by E is discovered, then another section of code is executed. Catch E. When begin transaction command is executed and an exception is caught before completion, the transaction rolls back using statement trans_a.rollback. Whenever an error occurs, database honors either returns to state it was in just before the error or finishes whole transaction. Transactions when recovering the data. Auto-commit mode means transaction is finished automatically even if an error occurs in between. Example is set auto-commit is equal to 1. Executing the command below disables auto-commit mode. Set auto-commit is equal to 0. Whenever a lock command is used, database is locked to current transaction only. Other transactions can access the database and perform operations after executing the unlock command. Conclusion. In this chapter, we have covered the following in detail. Basic concept: hoarding and caching. Cache invalidation. client-server computing architecture, transaction models, query processing, data recovery, data dissemination, communication asymmetry, data delivery mechanisms, broadcast disks, selective tuning and indexing, synchronization protocols,